in the room. So I'm Patricia, I'm one of the organizers of the school. So if you have any problem, come and talk with me. Carla, the other organizer, is arriving tonight. So tomorrow there will be me and Carla, okay? So I leave Daniel following his lecture. Ciao.
Okay, so is this microphone fine? Okay, so first of all, I'd like to thank the organizer for the invitation. It's really great to be here at this school and to be able to talk about this quantum network focusing more on the use of cold atoms. And so the idea, for me, it was really great to be able to do, to offer this mini course at this point of the school, because you had already 1 week that you saw the basics for atom cooling, so I don't need to go into that, okay? And you also saw just one talk about cavity QED, which also helps a lot for this talk. Nowadays, my first talk here I will focus on cavity QED as well, so it will help to really review some of the concepts. But the real idea here is to explore what you can do with cold atoms, okay? In which direction you can go to explore some applications, in this case, applications for quantum information. So the idea here is we are going to explore this concept of quantum network, okay? And this quantum network is just a collection of physical systems that are connected by what I call quantum channels. These quantum channels, they are able to transport and distribute quantum entanglement, okay? And these quantum sites, in principle, you can generate, process, or store some quantum information. So this is not saying much. It's just saying that we want to build these general systems to be able to do something with it, okay? And so this is just a general goal, to implement various quantum information protocols using this distributed physical resource. So this was summarized, this general idea in this paper of 2008 by Jeff Kimball, but it's been since then explored in different ways. So our motivation, as I mentioned already, is to explore protocols for quantum information. And there are two different sets of goals. First is the development of new technologies. And these new technologies involve quantum computation, which is just a new way to compute, and there is a potential for a great impact. And so there is quantum communication, which is the goal is to reach some kind of ultra security in communication. And for quantum sensing, try to get this ultra sensitivity. But it is also a new frontier of physics. Here, what we explore is this quantum correlated systems, larger scales, more than 2, and usually much more than 2. But there are also many questions in foundations of quantum mechanics on how these systems, they start to interact and how they work together in these networks. And finally, in a very instrumental level, but very important as well, is that we need to reach a new level of control of physical systems. And this field involves actually broad areas, atomic physics, quantum optics, quantum information. And when you see these areas, actually from atomic physics and quantum optics, look that you bring to this field these well-controlled systems, well-established experimental techniques, and also a good agreement between theory and experiment. But from the quantum information part, then you bring new problems, new approaches to see a physical system. And when you put this together, you see that you have this ideal platform to develop a kind of a quantum engineer and to test fundamental concepts. Okay. So before I enter into how things work, I want to discuss a little bit on what's the status now of this field of quantum networks, because it's advancing really rapidly nowadays. And this is a paper of this year with some review of the systems that are present operating. So this gives an overview of these green systems here are North America networks, quantum networks. These blue systems here, this is Europe networks, and this is from Asia network. This is the years from 2002 up to 2024. And see that there is some gap here in the middle. What happens that this initial stage here, that was the period where there was a development of this idea of a quantum internet, okay? And actually, these are the first experiments, but it took some time for these other networks to start to kick off. And what happened nowadays, we understand, is that actually to really build this kind of systems, you need to have some kind of a broader interest, let's say. I mean, you need to have some more funding, both government and private funding. So there are different things that you need to do. It's a different way to do, let's say, science itself. I mean, it's not just in one lab. You need to spread out your systems, sometimes in a city or throughout the whole country, okay? So it's a different type of way of doing things. And this was not actually, we could do that actually back at this time. And it needs some time to start, really. But so in Brazil, we are starting more recently. I mean, starting 2023, we have two quantum networks being built, one in Rio de Janeiro and another one in Recife. So the focus of my mini course actually is going to be around this period, which is really the discussion of the idea of a quantum internet, okay? I'm not focused as much in recent network. I'll just comment now, and then we may come back in the end to comment a bit more. And I also discuss in the end this Recife quantum network, because that's the one that I'm coordinating to the implementation, and this I'll use as a case study of problems and things that we find interesting to put in a network. Okay. And so just to give an overview, what we are discussing now about present-day quantum networks. For example, if you go to the US, you'll find many different networks. I mean, different cities like around Washington, Chicago, Boulder, Boston, and these are typically networks focused on quantum entanglement. Okay, so that's an approach that the United States end up moving forward. I mean, there are not as many networks focused in cryptography, but they are developing. So this DC area network is actually quite large, involving, I think, 9 different institutions with different sites inside each institution. And there are different specializations, I would say, in these networks. But you have also some large networks, like the one in China, where you have more than 20,000 kilometers of terrestrial links and 700 different KD links. KD here is quantum tree distribution. So this large network, you'll find parts of it working with entanglement-based systems, but mostly is a cryptography-focused network, okay? And this is already well developed. I mean, there is a whole engineering here. They have already standard equipments to be installed in these sites, and they have an architecture involve both the classical logic part, classical physical systems, up to the quantum physical backbone of the network. And you see different topologies that are explored with like circular topology to enhance to make the network more robust, and also this stars topology to actually use more efficiently some physical resource. And this Chinese network, it also has a link to satellites, okay? So if this satellite, it was quite important, this result 2017, I mean, they did also cryptography, but they also distribute quantum entanglement, and they were able at that time to distribute entanglement for more than 1,000 kilometers. And then this is just the basic to really launch a satellite network up to 2030. This is really a national project there. They are moving forward really in this direction. The most recent results, I mean, from this year, is that they announced their microsatellite system. That's the one that it can be built, many of them, to do really cryptography, to focus on cryptography. They also did, so they have now a small microsatellite, a small ground station, and they were able now to connect South Africa to Beijing by around 13,000 kilometers difference. So Europe also has a large project for quantum communication, involving many different, companies and institutions. And then you have this project to build this quantum communication European infrastructure and to do some more open quantum key distribution systems. Actually, all these parts here, they deal many times with different cryptography protocols. And so it's quite a challenge, really, to put everything together. And also they have a satellite project together. And this is just an image of what is viewed as this terrestrial segment for this infrastructure. And also there is a smaller set of groups working this quantum internet idea inside of this larger discussion of quantum communication, which also has a large focus on cryptography. And all of this I'm calling attention because I'm going to discuss only a subset of these many quantum networks that are being built nowadays, okay? When I'm focused with cold atoms, this means that I'm discussing networks which contain some light matter interface, okay? And this means that we are going to discuss how light interacts with quantum memories, and also, especially, quantum entanglement networks, okay? Because these quantum entanglement networks is where we can establish these entanglement connections between memory sites in different positions of the network. And so we are going to discuss more networks connected with quantum communication plus some kind of processing. And especially not focused on quantum cryptography. Okay. For quantum cryptography, the solutions nowadays that are given with this two sites protocols with some sort of trusted relay in the middle. It's possible to really expand for just this application. But there are many other things in quantum communication beyond cryptography. And when we are talking about build a quantum network with cold atoms, it means that we are interested in these other applications as well. So we are actually discussing this infrastructure for a multi-purpose quantum internet, okay? Not just cryptography. Okay, so what's the program here? Actually, I will not be able to even to cover all sorts of systems for quantum networks with atoms and memories, because this also has a large variety. But I will at least focus in two different effects. First, the first part is discuss networks based on cavity quantum electrodynamics. Okay, it will be really helpful, the lecture that Michel Brun just gave us, because it is really connected to this first part. And the part two, I will actually do quantum networks based on atomic collective states, okay? Because these are the two ways to enhance the interaction between light and matter. One is to use cavities, and the other is to use collective atomic states. So that's why you have two different parts. And finally, I will discuss this Recife quantum network. This is not going to be different lectures, okay? Probably I'm going to stay more in part one, and then a little bit less in part two, and this will be the faster one. So let's start then by the networks based on this cavity quantum electrodynamics. And then this was already anticipated by the last lecture. So we have different systems, many actors. There is Walter, Hiroshi, Kimball, Ramp. And at this time, this is already dated. Usually you divide these systems in microwave systems for cavity QED and optical systems. Nowadays, I think it's even more, there are many more actors here, because now you have nanometers and you have superconducting systems, and so the variety of cavity QED systems is really increasing rapidly. But over time, over a couple of decades maybe, these were the technical people working on the field mainly. And so this is Hiroshi that won the Nobel Prize 2012 for these microwave systems. But actually, for the networking, the focus of my lecture will be in the optical cavity QED system. So it will be in some way complementary to the previous talk. And so, somehow it's not passing. So we are going to discuss this atom cavity coupling. Okay. and just start with the cavity itself, okay? So for a cavity, we are going to consider a Fabry-Perot cavity. And for this Fabry-Perot cavity, we have some sort of a transmission spectrum. If you want to pass a Gaussian beam through it, I mean, Michel already anticipated, for these optical cavities, you can pass a system, you can pass a light field through it, okay? So actually there is some modes that couple to the cavity, and you see this coupling through the transmission spectrum of the cavity. And then you see this transmission spectrum with these different spikes here. And these spikes is every time your frequency, the frequency of your light matches your cavity length is an integer of the lambda over 2 given the cavity, gives the cavity length. So for example, here, for this particular system, the 104th mode will match the frequency of the cesium atom. It will be close to the frequency of a cesium atoms in the D2 line of the cesium atoms. And that's what's going to be used in the experiments I'm going to comment here. And we are talking here about a cavity that the separation between the mirrors is just 40 micrometers, okay? So it's really thin. But now we want to put an atom inside this cavity, okay? And now we start to deal with different frequencies here. One is the resonance frequency of the atoms, this omega A. And we have the omega C, that's the resonance frequency of the cavity itself. And the total energy will be then the energy of the free atom, energy of the free field, plus some interaction energy. For the free atom, then we are going to consider initially just a two-level atom, okay, with this level G and E. But for the free field, then you have really, you can have many photons inside your cavity. So you can have 0 photon, 1, 2, 3, and each of these levels will have some energy. But now we are going to consider the interactions, just dipole interaction. And what was already anticipated, that you can calculate what would be the electric field connected with the vacuum mode, which means 0. When you have 0 photons in your cavity, you still have some vacuum energy inside. Then you can calculate this electric field, and you are going to be inversely proportional to the square root of the volume. And from this electric field, then, and from this interaction Hamiltonian, you can have this coupling constant. And this actually has the meaning of a Rabi frequency. And then you can get the 2 times this coupling will be the Rabi frequency connected to one single photon. And finally, you can have even a resonant case in which you have this all frequencies the same, to be the same. Okay, so what you have here for the spectrum is that if you have this, without any interaction, you would have these levels, these energy levels of atom plus cavity, and you are consider here just the degenerate case. But once you consider interaction, then you split these levels. This was already discussed in the previous lecture, but just reviewing because it's important for everything that comes forward. And once you split these levels, then this gives some first a way to really address this strong coupling regime in practice. So let's consider this now, this strong coupling, which is consider just this realistic model for your system. I mean, you have this atom here. This atom can have some radiative decay of the excited state, but this radiative decay is for other modes that not the cavity mode, okay? Or you can also have some decay rate for the cavity itself, and you have this decay rate related with the time of flight of the atom through the cavity. And so you have really an open quantum system with some decoherence. And when you enter in this strong coupling regime, it means that your G0, I mean, your coupling, your Rabi frequency, your coupling strength is much larger than any of the decoherence rates. Okay, and when you reach this regime, then you have this strong interaction of one atom with one photon. In this kind of extreme quantum dynamics that was discussed already today. So just to put some numbers, this is the cavities is a node system from Caltech. This is not functional anymore, but this is the system that I have details from it. And the mirrors would be photograph of the mirrors will be something like this. I mean, you cannot even see well the separation between them, so it is just 40 micrometers compared with 3 millimeters of the mirror itself. This system, so a different thing that works in the optics regime with respect to microwaves, that the optical photon is much above the microwave energy. No? And so you can work at room temperature, so this is not a cryogenic system with respect to the mirrors, okay? So the cold atoms went later, but these mirrors will be at room temperature, but at vacuum. So later, when you enter with the cold atoms are isolated from all the mechanical parts that are at room temperature. And then you cool the atoms with light, and they are not affected by the temperature of the environment. But the mirrors could be, okay? But it's not that critical just because the energy of the photon is so much above thermal energy in general. Okay, so we go back to our system here. You see this coupling constant that gives the Rabi frequency. It's proportional to the square root, inverse of the square root of the volume of the mode. So that's why you need these such small cavities. So we are talking about a cavity length of 43 micrometers, but the transversal weight of the mode is like 50 micrometers. This is really a Gaussian mode. We have to think about two mirrors with some concave mirrors, and then you confine really a Gaussian mode inside this cavity. So it's like a regular cavity, it's just a regular Fabry-Perot cavity, but just very small. And then with these numbers, you can get this coupling to go to around 32 megahertz. And for the decay rates, you have like 2.6 megahertz for the spontaneous emissions in the modes outside outside the cavity mode itself. For the cavity itself, are around 3 megahertz. And for the first experiments, the time of flight was around 0.4 microseconds, okay, which would give a decoherence of around 2.5 megahertz. So we can reach, with this geometry, this strong coupling regime. But the thing is, how to see that? So we will see that using this effect of vacuum Rabi splitting, the effect that the energy levels separate once. You have the energy levels of your cavity. If you have an atom that enters in the cavity, these levels will shift. And that's the idea. I mean, you pass a laser through the cavity, okay? So you check the transmission of the cavity in a photon detector, and then you want to see this effect, which means that if the cavity is empty, you have just a transmission peak. If one atom is in the cavity, then you should see a split in the line if you tune the frequency of the laser. Okay, so this is a typical effect that we're going to look for in many systems. That's how we are going to characterize this strong coupling regime. Okay, so, but before we enter in the experimental pathway for this regime, I want to discuss, what's the idea of a quantum network with this kind of system? So, the idea starts with this idea of emitting in a controllable way one photon from an empty cavity. So, okay, so let's consider you have just an empty cavity, and then you include one photon in it. Okay. And let's say that you can control the reflectivity of your mirror in a way that you can extract this photon and give some special wave packet for it. Okay, so in principle, this is possible to do. I will describe a little bit later how you can do that. And it can be done in a deterministic way. You can extract photon from the cavity. But what this allows, if you are able to do that, is that in principle you can connect two different cavities with a fiber, okay, and store one photon in one cavity, and then insert this photon, release this photon in a controllable way, in a way that you can release it from one cavity and open the other cavity to receive it. And then you should be able to transfer this excitation to the second cavity. Okay? So broadly, this is something that is something that you want to do. To be able to transfer some quantum state from one system to the other. So how can this be done? So we can use one atom, okay, and use an atom that's not now a 2-level atom. We use a 3-level atom, so that you have 2 ground states. And one of the ground states is connected to the excited state and is resonant with the cavity. But the other ground state is not. So in some ways, you can just store an atom there in a state in a way that the cavity looks empty, because the atom is not interacting with the cavity at that state. But then you can come with a classical field on the side of the cavity, okay? And then you can even use classical fields to prepare even some coherent combinations of the ground states. You can prepare the system here, or you can just use it to transfer, to excite this atom to an excited state and couple with the cavity mode. Okay, so and that's how you can more or less fill up the cavity, because once you excite the atom, then the atom couples with the cavity, and the cavity can extract the photon. Okay, so that's the game. You just fill up the cavity with an excited atom, and the excited atom passes the photon to the cavity. And so, and with this in mind, then you can have this atom here, and then you can prepare some state to be mapped into a particular photon. And let's see if it's okay. And then what we want to do, we want to come with this field here and basically transfer a particular state to this transition here, and the cavity will extract this state and put it in a fiber and transfer it to a different cavity. In this other cavity, you need to do the inverse of this process in a way that once the cavity is filled with the energy of this photon, then you can act with this other field to map the system back to this coherent superposition of the systems 3 and 4. Okay, so this is a process that you can construct, okay? And this would be like, you need a single photon generator scheme which is completely coherent and reversible, and would enable this transfer of quantum states from one place to another in a network. So actually this work here in 1997 is the first work that discussed these quantum networks and discussed inside this process in a way that you can deterministically build a quantum state in one cavity and then transfer this state to another cavity. And this idea grew, okay? So there are other articles, for example, this one in 1995, in which discuss how you can, for example, if you trap many atoms inside a cavity, you can use the cavity field, actually, to perform quantum computation in this kind of system. Okay? And so there is particular protocols that were developed in this article, so that if you have a cavity QED system and you are able to really couple all these atoms with the same field, then you should be able to do processing. And so this idea grew then to this, and something that you can do processing in the sites with another way to really transfer these quantum states from one site to another. Okay, so that was the let's say the broad motivation to try to build these systems that to build this processing in a more distributed way. Okay, if you can do that, I mean, if you have such networks with memory, with processing, then you can actually do what's called a quantum repeater architecture. Let's say that you create some entanglement between two sites, and I will come back to this quantum repeater idea later. But this was a motivation for this kind of system. I mean, let's say that you have these sites here with some nodes that are connected. You have some entanglement between these sites. If you do some measurement here, you can actually destroy the information here, but project the information at the ends in an entangled state. So that's a way that you can actually extend the distance of entanglement. Okay, and I'll come back to this for why this is important. But I think what's more important here is like 1998, this date, is to understand that you are now talking about really just the sites with some capabilities, and they are connected by channels that you can distribute entanglement, okay? And so there were some requirements that were thought about on the time. I mean, you need some, for this, you need some light matter interface, you need some memories, and you need to perform some elementary logic gates. So the idea, more concrete, is this cavity QED systems with many atoms. And so what you have to have in mind is that these systems, I mean, that really follow that James Cunning Hamiltonian that was discussed already today. I mean, they are really good to build ideas, I mean, to make some engineering of the physical system, and then you can scale up your application. And this idea of quantum networks grew inside this environment of cavity quantum QED. But now let's go to the to the experimental pathway. First to the strong coupling, and later on how you can build these networks. So I already mentioned that I'm going to focus in the optical cavity QED, so there is a lot of works by Jeff Kimball and later by Garrett Ramp. They are the two that developed more this system. And one of the first systems in 1992 involved something that's maybe even closer to what we just saw. I mean, some atomic beam with cesium atoms passing through this cavity, okay? And notice that the difference here is that you have this probe light that's going through the cavity, and then you have these detectors here. So this probe light, you can check for the frequency, okay, of the light and see the transmission as a function of frequency. And then you have this cesium beam. What you see here, then is just, you see this splitting here. This is just a consequence of this vacuum Rabi splitting, a small splitting in the beginning. And what's the limitations here at this system is that you have, first you have a short lifetime of about 400 nanoseconds, but also you have a fluctuation in the number of atoms in this atomic beam. So in average, you have one atom, but you could have 2 atoms, 3 atoms with some probability. And this makes this curve, this dip less pronounced, okay? So that was a first experiment. I mean, I think the modeling took some time to understand the limitations of the system. It was in 1996. But the later step, the way to move forward with that was exactly with cold atoms. Okay, that's when cold atoms enter into play. Okay, so the magnetic optical trap, I think you had already many lectures. I mean, last week about how it works. Okay, but basically with this magnetic optical trap inside this vacuum chamber at room temperature, you are able to get this cloud of cold atoms to start with. Okay, and this is just a picture of a typical vacuum chamber with your cold ensemble here. In this case, is a vacuum chamber with rubidium atoms with a temperature of around 100 microkelvin and a couple of billion atoms here. So how can this be used? First of all, you can just substitute the cesium beam by a cesium mod. I mean, you can have still the atoms coming from just passing through the cavity, but coming from the cesium mod. So they are much cooler or slower. And just this difference, you just substitute the cesium beam by that, you already get, let's come here, you get much higher visibility for this dip here, for this vacuum Rabi splitting, and also better time of flight of 100 microseconds, but you still have an average number of atoms. So you still don't control the number of atoms that pass through here. Okay, so this also limits all the observations. Okay, this is just to call attention that this is from Jeff Kimball's groups in Caltech, this Gerhard Hemp in Germany, and so they start to more or less follow each other in this kind of applications for a while. You see, in the group of Ramp, they did more or less the same thing, but they did an atom fountain. So they just throw the atoms to the top, And this makes the atom much slower here when they pass through the cavity. So you have time of flights of larger than 100 microseconds. And so the next stage then is really to trap single atoms inside the cavity, okay? So that's a different step. So now you start with this, you have this empty cavity, and then you have this cloud of cold atoms. But then you need to now create a trap inside your cavity. So that's one of the tricky things that you can do in this system, is that you can build dipole traps, okay? Far-off resonance traps inside the cavity, okay? That's quite important because that's how you can really hold an atom inside the trap. So just to use the concepts of last week, so a MOT, magnetic optical trap, is a really good way to have a large cloud of cold atoms. But they are really, I mean, just a cloud at around 100 microkelvin, and what you want here is just one atom, okay? And you want one atom that's in a certain position for a long time, okay? And so you want to actually trap this atom and hold it in place. And to do that, so you can actually establish this far-off resonance trap here, and it's a different wavelength, okay? It's not, you don't need to make on resonance. This is something that you saw. I mean, for this dipole trap, you work very far away from resonance, but you have to use one of the other cavity modes to really build this trap. And then you release the atoms from the MOT and just hold one, in principle, here on the trap. And then you can cool it more once it's holded, just to make it your trap more stable. Look, that usually this dipole trap, they need a magnetic optical trap to start with because they are more shallow traps. So you can't start at room temperature. So you need to cool down up to the magnetic optical trap temperature, release, and then you can capture it in a second dipole trap. Okay, but to do that, notice that you usually use two different chambers. One chamber that has less vacuum pressure to just have a large cloud of atoms, and then you release to another chamber which has a much better vacuum, and so you have less collision with background gas, and then you can hold the atoms longer. Okay. So with this, the lifetime was increased to about 28 milliseconds. Okay, so this was even improved later, okay, with better cooling. I already called attention. After you hold your atom, you can continue to cool it. And with better cooling, they were able to increase this to 3 seconds, okay. Actually, the German group of Gerhard Hemp actually developed other techniques to cool the system and got up to 17 seconds in the system. Actually, these techniques from the German groups are very important. Note that they have this standing wave passing through the cavity. This allows them to actually capture the atoms out of the cavity and transfer the atoms inside the cavity deterministically. So they create this like a conveyor belt that just moves the atoms inside the trap and out. Okay. And so if this, they were able now to get really good vacuum splitting, Rabi vacuum splitting. You see that the picture is not it doesn't look like the two-level atom picture that was just splitting one peak in 2 peaks, because actually you have Siemens structure here, and so in blue you have the calculation of the full level of atoms or what the vacuum Rabi split should be in this situation. Okay. And you have the same for this German system. So I think here is rubidium atoms, while in the American system they use cesium atoms. But the results starts to be really close to each other. Okay. Okay, so what can be done here? What's the first use? The first use that this can do is to do the deterministic generation of single photons in this system. So in this case, you start with, again, with this 3-level structure, Look that we are talking about alkali levels. So these 3 levels is a very natural choice. You have the 2 hyperfine ground states of cesium or rubidium. These are the 2 hyperfine ground states that you find in most magnetic optical traps with alkali atoms. So these are already the levels that you use when you are going to trap the atoms. Huh? And you have one transition here, you see, that's coupled to the cavity, and the other is not. So your atom can sit there. Look, the atom is now trapped, but it sits in a different level, so it's not interacting with the cavity. And the cavity is effectively empty with respect to photons. But then you can come by the side with a beam to excite this atom to this excited state, and with that you can extract 1 photon when you do this process here, okay? So that's what I described in the beginning. That's the first thing that you want to do, is to extract 1 photon from the cavity. That's the first thing that you need to do if you want to build your quantum network, okay? So this was done in this paper here of 2004, but you can do that actually multiple times, okay? Because you can just come with a different field and excite to a 4th state in a way that you can do optical pumping, and the atom goes from here to here, okay? And then you can start the process again. You see, you can just come with these 2 classical beams on the side, and then use the cycles of extracting photons after the photons, okay? So you can use this as a single photon source as well. And it's not exactly deterministic, it's almost deterministic. I mean, in the sense that once you have the atom there, then you can deterministically extract these photons. But you still have to throw an atom and then hold it, and still have some things that you don't control in the system, okay? But you have a very well-controlled optical mode for this photon. Is in a Gaussian spatial mode. You can couple that to fibers. So there are already many of the things that you want. That could already be done here in this paper. So in principle, you can have this efficiency of 100% once you have strong coupling, even though, of course, this is not at this stage 100%. And so the thing is, how you know that you have single photons? Okay, that's one thing. I don't know. I think last week you didn't see much of quantum optics itself. Yeah? I think you focus more on the atoms. But so I would just recall some of these the basic notions that you need to understand what we are talking here. When I talk about single photons, what kind of measurements we are talking about? So we are talking about using 2 detectors, for example. And then you can extract this photon, and this photon generate a click here, for example, in T1. And then you can eventually get another click here at a different time, T2, okay? Look that, if you start to do this process many times, you see a collections of clicks at T1 and clicks at T2. And then you can define this difference between the time when you get a click in T2, a time when you get a click in T1. This is just this delay. And what's important is that if you have this coincidence, I mean, a click in T2 and T1, this should not be allowed if you have a single photon. That's the whole idea. Okay? You have a detector that's sensitive to a single photon, but one detector is not necessarily sensitive to 2 photons. I mean, if you get 2 photons in the same detector, it will just give a click. Okay? The same as 1 photon. But then if you use 2 detectors, and then you split, then you can have 2 clicks if you have 2 photons, okay? So you need to calculate, I mean, how many clicks you would have. If you have 2 photons, how many coincidences you would have, okay? But the problem is that if you have a pure single photon, then you should have no coincidence, okay? And that's what you should see if you put a weak laser pulse in this beam splitter, and then you get you do this kind of experiment, you should see these peaks here, because you come with different laser pulse, you should see a function more or less like this. If you have different pulses, I mean, they can click at different times because you come with different pulses, but at the same time, there is a probability that at 0 you have something, some coincidence. However, if you have a single photon source, at different times you should have a probability to generate one photon in one event and another in another event. So there is a probability to generate at different times. But at 0 time, this should be 0. Okay? So that's the general idea. And these are the experimental results that you get from the system in the previous slide. So you have a really decrease in the number of these coincidences. It doesn't go completely to 0, okay? So you have a suppression of about 20, but it's not ideal because you still have a probability of having 2 atoms in the cavity. So you can have 2 photons if you have 2 atoms. So there is still some imperfection here. You'll find the same kind of experiment in parallel with the German group, okay? So they were also able to do basically the same process, and then to get this sequence of single photons, and to get this what's called it's called the G2 function. Is this second order correlation function that goes to 0 at the 0 delay. And the 0 here means that you just have 1 photon. You cannot split that in the beam splitter. But you also have, in the same way as the Caltech group, you also have some background that comes from imperfections, okay? And for example, one of the imperfections is two atoms in this cavity. But you see the time of flight here is also very large, 18 seconds. And I think what was very cool that they did in 2007 is to use this process actually to generate, this is for the German group, to generate a train of 300,000 single photons distributed in 30 seconds, okay? Note that the time is so large that you can actually look at the system and you see that you can have something that's larger than what's expected for 1 atom, because this is when you have 2 atoms in the cavity. So if you have enough time, you can wait until the second atom leaves, and then you start to have just 1 atom really in the system, okay? And that's this way you can really improve these correlation functions to leave it closer to 0. So this starts to get a really well-controlled experimental system over time. It's interesting that when I'm now moving forward to a quantum network, and now actually the competition between the 2 groups stops, because what happens at the group in the US, I work in that group, so I will comment in some of my work in that group later, they were actually never able to duplicate the system, okay? Just because the experimental complex was large enough, okay, that if you learned a lot of the first system, you were not able to build the second system as well. So that was really a complicated issue. And they have 2 labs. They have 2 traps, but one of the labs didn't have a trap that was as good as the first one. And then they were never able to really talk the two systems. But the German group from Gardner, they succeeded to do that, okay? And so in 2012, they finally did the experiment with the system in a particular cavity, okay? And they were able then to extract this photon and then include this photon in a second cavity. So they were able to do finally the process of start with some state, pass through the photon, and then insert the photon in a separate cavity. And they've been improving the system a lot since then, and especially, for example, to transmit arbitrary states from one cavity to another, to do teleportation. I will focus in just a couple of applications here. First of all, here already you have this transfer of states, okay? So now you see that here's just a simple picture that I called attention before. You just need the 3-level atoms. But let's say that you want to transmit really a state from one cavity to the other, then you actually want a superposition of Zeeman states. This superposition of Zeeman states, then you can map in a superposition of polarization states of the photon. And this goes to the second cavity, where you have an atom in a particular Zeeman state. And then this superposition of polarization states leaves the atom in the second cavity in the same superposition of Zeeman states that the atom in the first cavity was. Okay, so that's how you can really transfer an arbitrary state in principle from this cavity to this other cavity. And then you have to do some kind of tomography to check if this is the proper state and what's the fidelity of this state with respect to the state in the original cavity. Okay, so that was really the general idea that was people were looking for in 1997. So it's a good number to have in mind. 2012 in 1997, so this is 15 years, okay, of improvements in the experimental system. But there are other really impressive things that have been done since then. One is to do some logic gates in this kind of system. So I will just explain the general idea, and then at least for you to have a notion of what can be done in this kind of system. So here they were able to first to trap two atoms, okay, in different nodes of this dipole trap. Okay, so in a dipole trap you have this static wave, and this static wave has different minima, and then you can trap atoms in different places of your static wave. For this kind of process using cavity QED, the interaction is done through the cavity QED mode to the cavity mode. And they don't need to be close to each other, okay? The interaction is mediated by the cavity field. So in a certain way, for the lets of atoms is a non-local interaction, okay? But then, what's this logic gate here, what it does? So first of all, they were looking at a system where you have these two atoms. The atom can be in two different states of the ground state. So it can be in a state down or up, one atom or the other, and the cavity will be resonance only with an excited state in the up state of the atoms. And then they bounce a photon. I mean, it comes a photon through a fiber, for example. It bounces and come back. It can be free space or fibers. And this logic gate does the following. If you have the two atoms in the upper state, it continues in the upper state, and the photon doesn't get any phase shift. And if you have one atom here in the other in the other state, it doesn't do anything. But if you have the two atoms in the down state, then it gets a shift here of pi. Okay, so that's from a logic point of view. That's what this C0 logic gate does. However, how you do that in practice? Then, first of all, it's important that what you have here is just that effect that's responsible for the vacuum Rabi splitting. Okay, it's a cavity that's on resonance with an atom or not. And just to call your attention, if this paper here, I think from 2000. Oh, I didn't put the reference here, but it's from Alessandro Villar. Okay, it discussed what happens with an optical cavity, an empty cavity. Okay, and then you come with an incident field, and then you have this reflected field. And you see here that when you calculate what happens with the reflected field as a function of the detuning of your field with respect to the cavity, you see that at resonance, okay, you should have some absorption. This depends on the reflectance of the mirrors. But the phase shift, okay, on the reflected field depends on where you are in the resonance. Okay, so you have a phase of pi, okay, if you are in perfect on resonance, but you get a phase of 2 pi or 0, you see here 0 or 2 pi, if you are out of resonance. So you don't get a phase if you are out of resonance. And what happened here, you see that all these situations here that you have one atom in one of the up states, the cavity is in resonance with one atom. And then the cavity, since it's resonance in one atom, it's not resonance anymore with a photon that's in this, with zero detuning. And then you get out of resonance, you don't get any phase shift. But if both atoms are out of resonance in the cavity is empty, and then the reflected field gets a pi phase shift. Just to make sure, this is not something very peculiar to cavity system. Cavity system is just a resonator, okay? So this is actually something that you will find in any resonator. So this is an LCR circuit, and then if you want to excite this circuit with certain some oscillating function, you get that. You get a resonance, and then you get a phase shift if you are on resonance or if you are out of resonance. Of course, the phase shift itself depends on what quantity you are looking at, okay? In this case here, you are in the reflected field, and that's why you have the pi shift. But this is a general property of any resonator. The only thing that you have here is you are on resonance or out of resonance with the atoms. And then you get this phase shift or not, okay? But of course, this is not also easy to prepare or to check how you get this phase, how you are going to get that something flipped by a minus sign, okay? Then you enter in a different set of experiments that were done before this logic gate, which is how you can actually store Bell states here. Because you have these two atoms here, they can be independent states, but they can also be in an entangled state, okay? And then you can use this cavity mode to build these entangled states between these two atoms. And this was done in previous work. Actually, what was done here, you see that you have these two atoms here. So this is 2017, this is 2018. Actually, most of the work is actually here. This is a step after this. So what you have here, you see this, you have these two atoms, and you can excite the system through the sides with these other fields. Look, this is a Raman, what I'm telling you, it is a Raman pair, just for you to have in mind. I described some process in which you have optical pumping. You come with a classical state here, and then you can have some spontaneous emission in this other branch. If you put a cavity here, this is not spontaneous emission anymore. This is an emission that is really enhanced by the cavity. However, you can also come with two different fields like this. Okay? Very far away from resonance. And this can do a Raman transition between these two states. This kind of Raman transition, then you can do anything. This looks like a two-level system. Really, you can do complete coherent interaction. So you can, for example, you can start with an atom here, and then you can create a coherent superposition between these two fields. If you generate a pi/2 pulse, effective pi/2 pulse here, or you can completely invert with a pi pulse, so you can do anything. So that's a well-known way to control a two-level system. And you can do this with these lateral channels here using Raman pairs of pulses. That's when you start to discuss the system using our circuit, a quantum circuit. That's where you have these rotations here. You see rotation by pi/2 with a phase of y. You have this rotation of pi. These are always controlled Raman pulse that you apply in the system. And then what can be done? The first thing is how to prepare the system in a particular state. I mean, to prepare the two atoms in the down states, you just need optical pumping. Okay, you just do optical pumping to a level that it decays spontaneously down here to here. To prepare this system here with one atom in the up state and the other in the down states is a little bit more tricky, but it's doable, not a big problem. But after you do that, then you have a protocol here. They developed a protocol to actually entangle them. And the protocol starts always with this pi/2 pulse. See, if you create a coherent superposition, a single atom with a coherent superposition between these two levels, you end up with something like this. You see, if you start with the two atoms in the down state, and then you apply a pi/2 pulse, you end up with a certain probability of the two atoms being the up state, a certain probability that you have one atom in the down state and the up state, one or the other, and a certain probability that both atoms are still in the down state, okay? And then you start here, and from here, then you can come with one photon like this, but this photon is not now in a particular polarization. It comes with a superposition of two polarizations. And if one atom is in the upper state, then it doesn't suffer a phase shift. However, if both atoms are in this down state, then it suffers a phase shift. So it changes the polarization. And then you can detect this change of polarization in the two detectors here. So this is a non-polarizing beam splitter. The photon goes in the cavity, bounce back, and this is a polarizer. And then you can measure the polarization of the photon. And then with this, you can see if the atom is here, and then you can throw this out. This is this part of the diagram here, is that you measure, you send a photon, you measure if it's in a particular state or not, and then you throw out the situations where the atom is down here, okay? And then you do a pi shift. You see, you do a pi pulse with these Raman fields, and the pi pulse transforms this up state in down, okay? And then you go with another photon and throw out this down, and then what is left is this state here. You end up with a state where you have just one atom in the up and the other in the down state. But in a coherent superposition of the two. So that's how they can really measure, they can really prepare a Bell state, and you use a similar procedure to check if you really has that specific Bell state. From one Bell state, you can create two others for the symmetric wave function. The asymmetric one, you have to start with a different initial state. So, but this one thing that I want to highlight, in this kind of system, you can actually prepare all four states of a Bell base, okay? So you can get a family of entangled states. And why is that important for what we are going to discuss? Is because you see this small change here in the phase, you can actually see it if you have these Bell states, because for the Bell states, this change here in phase will flip the signal of these Bell states, and actually will turn this phi minus states in a phi plus, and the phi plus in a phi minus. And that's how they detect, okay? They detect the following, they prepare all four, each of the Bell states, and then they do this operation here, and then they see the output, and then they see the flip of the Bell states, okay? So that's the way how you can detect it by detect that your Bell state changed. But that's a very interesting step because it goes also in that direction that you can build a buffer. Né? You can have more atoms inside a cavity system, and then you can start to do some information processing there. That's the whole circuit diagram for this system with this Bell state measurement, generation, the gate, and then the analysis. Okay, and this is the last result that I'm going just to highlight. Is how you do this cross cavity. That's a nice trick. You can build these cavities that are in a cross geometry, okay, and in a way that once you excite the system from one ground state to the excited state, the other transition is resonance with one transition resonance to the cavity, and the other transition resonance to the other cavity. Okay, so actually, when you go in a three-level system from one state to the other, you can transmit photons from one cavity to the other, or the other way around. Okay, so that's a way to really move forward to some more complex geometries. Okay, so it's important I already call attention to this timeline. So we have 2020, so we have more than 20 years of developments of this kind of system, maybe a couple of decades. And I think this is developing in a very consistent way, even though, I mean, there are not many groups. I mean, I just quoted results from two groups, one in the US and the other in German. So there are not many groups competing, I would say, in this line of research. However, all these ideas, they can be translated to other systems, okay? And that's where it gets also very interesting. So you have these other cavity QED systems, which is interesting, okay? And So first of all, you can try to work with ion traps, okay? So this is an interesting perspective. I mean, we're talking about a lot of technical difficulty, okay? In principle, you can always think, okay, I can have an ion trap and then just put a cavity around it and it should work, but actually it's more tricky, okay? So the cavities are different. What we are discussing up to now were just a cavity with neutral atoms. So you just have this mirror there, and then you have to do the coupling with the fibers and the mirrors. But when you have an ion trap, then you have all the electrodes in the trap. So you have a lot of mechanical parts, so it makes it harder. And I mean, many groups tried for a long time, and they've been succeeding, but it's just at a slower pace, okay? But this would give a new perspective for this kind of system, no? Because this ion system, they have advanced atomic clocks and quantum computers. So there is already a technology that is developed to do quantum computing just with these ions. And if you are able to really add the cavity, then this would allow all what you do in these small processors to really connect it to others. No? And so that's a broad goal, I would say. And there are different approaches to it, okay? This is just one of them. No? So this is a system that already is, this is from 2004, Walter's work. Already he could do this ion trapped cavity. Let's see if, okay, so it works, okay? As I mentioned, it's very similar to the cavity QED with neutral atoms. You can do that measurement for the detection, for the probability to get 2 photons, and then you see that with 0 delay, it goes to 0, and then you have this constant probability to get with a certain delays. No? But now you have these more complex systems, but in essence, it's quite similar to what we had before. I mean, and this is another example, but this is in a way that already they explored to do some deterministic single photon source with the single ion. And they were also able already to do this quantitative transfer from an ion to a photon. This is already from the group of Heiner Blatt. No? So we are talking here, this is 2013, I believe. And you see now, you follow really a procedure that's close to the cavity QED with neutral atoms. I mean, you have this superposition between 2 ground states, and then you need to be able to pass the superposition to a superposition of polarizations of the photons, and that specific superposition, that's what you extract from the cavity, and then you can check, okay? You can check that you can transfer this state from the ion to the photons. So there are many techniques to characterize very well this state for the atom, and then after you characterize the state for the atom, you can characterize the state for the photon, and then check the fidelity between them. Look, all the time, every time that you have this state transfer from an atomic system to a photon with a cavity in the middle, you see this is always challenging because you have birefringence in these cavities. So not necessarily you have the 2 polarization coupling in the same way. So usually you have to really work hard to control that, to be able to really map this atomic state to a photonic state, okay? Because you really have to fight a lot of technical imperfections. So, Michel Bruno already mentioned this cavity QED with nanometers. That is a really interesting system, because now, I mean, first of all, when you have a cavity QED system with a single atom, so you have your quantization, it comes from the quantization of the material system, okay? So you have just one atom can release just 1 photon, okay? But actually, this works for anything, okay? So if we can single out any quantum emitter, you see them emit just 1 photon, okay? So it can be a quantum dot, it can be a vacancy in a diamond matrix, it can be almost anything. But if you are able to, with your optics, to isolate a single quantum emitter, you have a source of single photons, okay? So this is something important to have in mind, because I would never classify single photon source as something that is artificial. Okay, a single photon source is natural. We just need to really look in the right way. But then your photon also actually is going anywhere. Okay, you just what you're saying is that if you get just 1 nanometer and you try to see the probability to emit 2 photons, that will be low. But the photon is going anywhere. To use it, then you have to do something else. And here's one of the things that starts to do, the 2000s. You can build a cavity around one of these nanometers. So one of the first ways is to build these micro pillars here in the group of Yamamoto. And he showed here in 2002 that they were able to get 38% coupling to this cavity. So you have your single photon going anywhere, but then once you put a cavity, then you start to have the cavity QED effect. Then the cavity starts to drive the emission in the mode of the cavity. And that's really critical for this system, okay? But then you can see here that this is the same measurement of the probability to get 2 clicks around delay 0. You see that you can get something really low here. And how low? Very low. Here is 0.10. Nowadays, you can get much better than that, okay? I will show some results for recent systems like this. Let's say if I have right in the next slide. Well, this is one of them. This is another system. I'll show some the best numbers nowadays for this kind of systems, some of the best numbers. But before that, it's good to have in mind that you have these nanopillars, but that's not the only solution. You can have actually any kind of cavity. Here they put some photonic crystal. They create a structure here around a quantum dot, I believe here. Yes, this is a quantum dot system. So they can build a photonic lattice so that the emission goes in a particular direction that you can control. Notice that you typically start with something like this. You have many quantum dots, okay? And then you have to choose some place where you can really build your cavity around. So if you have just this ensemble of quantum dots, you would have a spectrum that's really broad like this. So here it goes from 1,050 to 1,000 and maybe 1,300 nanometers. But then you start to build these cavities, and then you start to have these Q factors of around 20,000, 16,000, and then you see that the line becomes very much thinner, okay? But they are still at different places. This is something tricky that I'm going to discuss. One thing that is more tricky in these solid state systems is that you really need the cavity also to control the wavelength of the emission. Every quantum dot has a different vicinity, and then your mode, the emitted mode in terms of frequency and also in terms of shape, it's a bit different. And the cavity needs to control everything, frequency and also the mode, the spatial mode. But this is a measure of vacuum Rabi splitting in this quantum dot system, okay? So this starts to characterize the strong coupling, okay, of the emitted photon, the nanometer, and the cavity mode. And you can even have this typical picture where you have the quantum dot, you have the cavity, and you have this interaction region, have this splitted crossing. Okay, so this developed up to some commercial sources. Okay, so you have this company. Candela is one of the company. I don't think it's the only company here. You have the Candela, you have Sparrow Quantum in Denmark. So these are already some established companies. And you see that the cavity for the Candela system is already quite different from the nanopillars, but they have very good numbers for their sources. And the cavity for the Sparrow Quantum is already also very different. This is photonic lattices. But you see that And what's the motivation here is, I mean, I've been talking about quantum networks, but if you have a deterministic single photon source, and that's the goal here, you see, if you have a single atom inside a cavity, you can build a deterministic single photon source. But if you have a nanometer inside the cavity, you also have a deterministic single photon source. But then you don't need to trap this nanometer, it's always there. When I say always there, you have also to be careful because these materials sometimes degrade over time. So there is a way to deal with them, to keep them alive for a long time, okay? But the motivation, once you start to have deterministic single photon sources, is to do some kind of computation. So there are these proposals to do quantum computation with linear optics, and what you require here is really single photon source, okay, and photodetectors, and also beam splitters, phase shifters. It's important to have in mind every time I mention this proposal, because this was really inspiring, I would say. But actually, this proposal, I mean, it's really hard to scale up, okay? The physical resource grows very quickly. I mean, the number of photons and the number of detectors that you need. However, it's been evolving, okay? It's not stopped. I mean, this protocol is considered nowadays not scalable, but there are new versions of this protocol that are more scalable, okay? And actually, once this company starts to develop this technology, they more or less focus on this quantum computation. Not all. I think that the Denmark company, I think the focus is more in quantum communication. Then there's a parenthesis that there is something that we need to say. I mean, for quantum cryptography, I said that I'm not going to focus on quantum cryptography here, okay? But for quantum cryptography, usually the most common systems to use attenuated laser pulses, because they are simple to use, and attenuated laser with a diode laser is really cheap, and then you can get a very high repetition rate, okay? But an attenuated laser has a problem, okay? The problem is that it is attenuated, okay? So you have to work with it attenuated. So you can have even a high repetition rate, around many gigahertz, okay? But you have to attenuate it, okay? But not this source. The single photon source with nanometers, you don't need to attenuate. Actually, you work with it at maximum saturation. So it doesn't have this fundamental limit. And presently, it's getting closer to being competitive, even with attenuated lasers for cryptography. Okay, it's basically a factor of 10 in terms of repetition rate. Okay, so but the tendency is that they will pass an attenuated laser because just they don't have this fundamental limit, and they can grow from that. So I'm just calling this attention for you to appreciate the results from this. So you have this company, and then they have some proposal for a quantum computer based on these quantum dots. See, there is always a problem here that these quantum dots, they have a difficult time talking to each other. So usually this kind of initiative, you use just one quantum dot, and then you take many photons, and you delay these photons. So when they say 12 photons, it means 12 photons from the same dot. It's just that you are delaying them and then entering the computer simultaneously, okay? This is a process that is, Candela, I think they have a processor with 12 photons nowadays. But this, I mean the group that has the most number of photons, I think, is a Chinese group of Jian. I think they are around 100 photons, but always from the same nanometer, okay? But I think it's impressive, these numbers here, okay? So they can work with the single photon source at 1 gigahertz clock to generate the photons. And they offer you, I mean, they have losses and many things, but they offer typically a generation of 20 megahertz. These are the kinds of numbers that I'm saying that they start to get competitive with attenuated laser pulse. Because in attenuated laser pulse, they can work at gigahertz, but then they have to attenuate, and then they will get to the hundreds of megahertz or tens of megahertz. While now you have 1 gigahertz here, you have already more than 20 megahertz, but actually, if you solve the technical issues, you can get to the 1 gigahertz, okay? This indistinguishability, you have to be skeptical a little bit. This is from one photon from the source with the next photon, okay? So it's not two different sources. I mean, it's not the indistinguishability from two different sources. There was a paper this year by another company called PsiQuantum in the US that they claim to have two different sources with more than 99% indistinguishability, okay? But not these numbers are just for the same source, which is also important. Look, if you control the decoherence of the source itself, that's what gives you the number of photons that you can extract. So when you have this company, the Candela, with 12 photons, and the GUA-PAN group with 100 photons, so that's the difference. How many photons can you extract and still be indistinguishable from the same source? And so these are really impressive numbers for these sources. And then you can do many different things. I mean, I already mentioned quantum communication, quantum computation, but actually, these are getting to the point where you can really use the single photons for metrology, just to control the flux of light. And then if you want to have a really very well-controlled light for, I mean, to calibrate power, for example, that's the kind of system that you can have. Okay, but this is just one interesting system that use all the physics of cavity QED. But you also have these superconducting junctions, which I already mentioned in the last lecture. I'll just give some highlight. I still have some time, so I can use this end just to, it's more like 10 minutes. Huh? Okay, I'm just commenting a little bit here. For these superconducting junctions, what you need to have in mind is that you have a system that was proposed in this article, well, which is just the Nobel Prize of this year, actually. And they propose in a way that they show that the Joseph's junction, the flux here, the energy of this junction, can actually be modeled by a two-level system. Okay, so you have a particular circuit, and they showed how you can measure these energy levels here in a way that is doable. Okay. And then they are sensitive to this two-level system that's formed inside this new structure that's called this transmon. But what's interesting is that you can get this transmon, and then you can actually build a microwave cavity around it, okay? And then you can couple, okay, this microwave cavity with your transmon, and then you can have a free cavity energy, okay, your cavity without the transmon. But then you have this free transmon, okay, that's more or less a two-level system with some nonlinearity here, but it's roughly a two-level system. And this will be eventually neglected. And then you can have a way to excite your whole system here, and let's say, and you have some interaction, okay? You have some resonant interaction between the transmon and your cavity mode. And then when you put everything together, you end up with the James Cunning Hamiltonian in the same way, okay? But it's a different system, because now you can actually, so, and then when I say that you are in this James Cunning Hamiltonian, it means that you can see vacuum Rabi splitting, for example, when you excite the system, okay? So you have a resonance without the transmon there, but then when you have the interaction with the transmon, then you see this splitting in the same way that you see in the other cavity QED systems. And so you can have this strong coupling of the single photon in microwave with the superconducting qubit. And then you can actually work with different number of photons there. Of course, Michel already mentioned the numbers are quite different for the coupling strength, for the Rabi oscillation frequency, and the decay rates. But then you can actually build from that. You can build different computer architectures. Okay, so actually you can increase the complexity. So here's a situation. See, you have one cavity with two transmons. So you can start to build on similar ideas that you had with the atom, or more atoms inside a cavity. These I just mentioned a couple of numbers for both the 3D optical system, 3D microwave system, and this kind of of superconducting circuits. I'm not going into these numbers. They're not very far away from each other, but they have some numbers that are really better for the system in terms of decay rates, for example. And then you end up with this kind of, you can build these architectures. Here are qubits, these circles here, and then you have this coupling bus with some of these lights, and then you have these readout resonators, and then that's how you get these computers, nowadays, these superconducting computers. And so, I mean, I think it's important to mention this because, I mean, even though there is this long time scale to develop the cavity QED for quantum networks, I mean, all these ideas, I mean, they are already, I mean, they fed other systems, and the other systems, they basically develop with a different time scales as well. And with this, I mean, I had my first lecture. In the afternoon, then we start with these ensembles, okay? So, so questions? It was too clear, too fast, asked the same question. Okay, go ahead. Let's see if he... Oh, let's see if it's on.
When you were talking about the implementation of a CNOT logic gate, you remember that? You talk about a little of resonance control of two-level systems. I really appreciate you. I really appreciate if you maybe go a little deeper in this idea.
This idea here?
Yeah.
Yeah. So when you have a system like this, you are very far away from resonance. Okay. You can work in this system as a three-level system, and then you can write down the excitation. Initially, you can even consider the decay rates, but if you consider just the coherent excitation here, okay, you see this big difference here in the detuning. Okay? What this means is that you have some very fast oscillations, very fast dynamics related with the excited state, okay? And these end up leading to an approximation called adiabatic following, which means that when you excite the system like this, all the quants that's related to the exact state, they reach their stationary state really quickly, okay? And this allows you to eliminate from the dynamics the excited state. It's just it's always in a certain stationary state. When you do this, you eliminate formally from the system, but actually when you have these large detunes, the probability that the atom will be here is getting smaller and smaller and smaller, okay? So this adiabatic elimination, eventually, you can get rid of this excited state, and you end up effectively with a two-level system with these two systems here. Actually, you end up with a Rabi friction that's proportional to one of the Rabi frequencies, the other divided by this detuning here. So you end up with an effective Rabi frequency between these two levels, okay? But this is a slow dynamics when compared to the dynamics of anything that happened to the excited state. It doesn't mean that doesn't happen anything, okay? So you have coherence here, you have coherence here, okay? But it's just that it's always more or less in a stationary situation. All the dynamics moves slowly with these other Rabi frequencies.
Okay, thank you.
Okay.
Hello, thank you for the class. About the transpons, I didn't understand why to account for them as a two-level system when we have a lot of energy levels. I mean, we can enter in resonance with this between 0 and 2-level system. I mean, 3-level system or some approximations like that.
Yeah, so basically, to have this resonance of the cavity with a particular two-level system, you have to work for that. I mean, usually you need, for example, to apply sometimes a magnetic field. It's like in the start shift that Michelle mentioned before, but you can put a magnetic field, for example, to separate the Zeeman structure, and then to leave just one Zeeman transition from the ground state to the excited state connected with the cavity. You can do that, or if you want to explore, like I mentioned, the transfer of a quantum state, that you want to explore some coherence between Zeeman levels, then you can not apply the B field and leave the Zeeman structure degenerate. Then you don't have two levels, really, you have a degenerate two levels. Okay? But usually you really need a system that the other modes of the cavity are not resonant with any other atomic system, atomic mode. This is really a powerful tool. Just to mention, I mean, if you can use that to do manipulation in a very strong ways. For example, sometimes in the system where you have two atoms, if you apply, you have two atoms and you don't know which Zeeman state they are, but you need to prepare the atoms in that up and down states, okay? That up and down state, they are in this extreme level here, okay? But you have here some excited state. I'm not drawing here all the details, but, and you can put the cavity resonance with only this state here, not the others, okay? And then if you come with some, and then you can come with some optical pumping here. You can do optical pumping using this probe light. You see what's going to happen. There is two atoms that you don't know where they are. So the first one that gets here, the pump light is blocked because it gets out of resonance. So that you can use this fine effect. You see, that's how they can prepare different superpositions, because they can take one atom here, the first atom that gets here, this light is stopped, and then they can transfer, for example, this atom to here, and then they continue to do the optical pump until it goes there. You see that you can really even discriminate the Zeeman levels, but then you have to put some magnetic field to use that. Yeah. But it's really it's just one particular frequency. If you have other levels with that frequency, okay, but it's typically just that frequency for the cavity.
Okay, thank you.
Okay, you're up. No more? So we can have lunch and continue later today.